Hi everyone, welcome to a new segment that we're calling TinkTech. I'm your host Eugene, and we've got
Andy here as well.
Yeah, so just to give you guys a bit of an idea of what TinkTech is going to be, we were discussing about transfer of knowledge from us to, well, you guys, the viewers. And we thought that we would really start to explore the underpinnings of all the technologies in the 3D printing space.
Yes.
And that's us getting nerdy. That's us getting
nerdy
into the mechanical and engineering side. That's us talking about things like Hotends, how resin actually fundamentally works, and all the different type of technologies. Us getting into the gantries, and I'm just throwing jargon around everywhere at this point in time. But yeah, I hope you guys join us on this new segment called TinkTech, and we're just going to nerd out with regards to stuff. So first topic we did pick, one that is probably the most important element of the FDM or FFF 3D printer space. So that's the filament-centric technology. Well, Hotends. We've got a couple Hotends in front of us, and we'll probably put an overlay because there's so many different type of Hotends on the market. But what we really wanted to talk about is how Hotends are designed, what makes them important, what features and functions must somebody do when they're designing a Hotend to make them reliable and usable and durable. And we just want to jump right into it. Yeah. So, Hotends, what are their functions? What do they actually do? Well, what does it do?
Well, I'm sure maybe everybody that has probably seen a 3D printer probably has a gist of how it functions. Essentially, if you look at it, it's where the filament goes in, which is the plastic. The plastic goes through this Hotend, and it gets heated up and it deposits the plastic onto the bed.
Yeah.
So that's like a very general gist, but there's actually a lot of design work that goes into one of these. Well, I'm not the one that designs our Hotends.
Yeah. So a Hotend has a couple components that's actually quite important. We can define it as two main areas of focus. You've got the cold end, which is the part that's supposed to stay as cold as possible so plastic doesn't get soft. And then we've got the hot end, or the hot zone of the Hotend. And that's the part that actually melts the plastic. And then wherever it interfaces, the portion that the two zones meet, that's usually what is called the heat break. Something needs to go in there to prevent the heat from creeping up, softening the plastic, and isolating the hot part from the cold part. Now, there's a billion ways to design for that. Like, we've got 3 Hotends in front of us, which are 2 of which are the Tinkerine designs, and one of them is it's a super old design by a fellow out in the US, and he makes it a Hotend called J-Heads. I don't think these are actually made anymore. This is a super legacy design, and one of the most reliable designs when that was first introduced. And the idea is that we need a way to isolate the hot and the cold. Like, the hot can't translate and transfer heat over to the cold. And there are a whole bunch of materials for that. Insulative materials. There are thermally non-conductive materials. There are titanium. There are stainless steel. We've heard about all metal Hotends. We can even put a photo of the all metal Hotends up. And those operate off the exact same principles. The difference is that it uses only metal components. So instead of it being super insulative, they find materials that are super bad at conducting heat. And the heat break, the portion that separates the two, that's usually titanium or metal, or stainless steel. And that is milled so thin where the heat just can't pass through. So when we're talking about thin, we're talking...
Is that even possible?
Yeah. The wall thickness of where the heat break portion is as small as 0.2 millimeters. The wall thickness of the part. Which means it can only transfer so much heat away, and then when you have a fan blowing, heat just can't go up.
It just literally dissipates.
Yeah. So In the case of the J-head, it uses an insulative material, PEEK.
Yes.
One of the thermoplastics that people are trying to print with. And so you have a really good plastic, a thermoplastic, that insulates the heat of the nozzle, separates it from the cold zone, and it actually doesn't transfer the heat up. You still need a fan. Yeah. You absolutely still need a fan to cool it. Actually, with all hot end designs, you need a way to cool the cold end, right? Fans are a good way to do it. But if you have a heated chamber, and we'll talk about a heated chamber on a totally separate episode, then you will probably want water cooling. So being able to take the water, bring it outside, exchange the heat, and then bring the cold water back in and keeping that cold end cold. So the problem with a hot end that has a thermoplastic that is insulative, that prevents the hot end from transferring, is that you can only go below the temperature of the melting point of that plastic.
A PEEK has 300?
It has a softening temperature of between 275 and 280.
275 to 280.
Yeah.
So if the fan was not working on this hot end, on the printer, then it would have just melted the PEEK.
Yep. So you can only do plastics that is able to go up to that. So you're looking at PLA and ABS only.
Yeah.
And so the idea of an all metal hot end is supposed to give you broader range of application. So with regards to the hot ends that we build, there's a PEEK insulative component to it, right? And so that is the component that separates the hot part from the cold part, and then we have the fan blowing on it.
Yes.
With regards to a lot of the other hot ends out there, the E3Ds, the Mosquitoes, and all the other ones out there, they also still need a fan, but they're all metal. In that, so that they can start to do the Hotends, the PEEKs. You can actually print with PEEK. Yeah. It's a super strong material.
Well, it has a higher higher. If you can heat it higher and it has a higher resistance to this, then all these materials can be introduced, right?
Well, there's nothing that will melt.
Well,
so you can put the hot end all the way to like 360, 450 degrees, and the only thing that you would have to worry about is maybe the aluminum heater block. Melting. So a good segue, I guess, from there. Give me a second. Is all these hot ends are designed to dissipate heat.
Yes.
On the cold side. So most of the hot ends that we have seen in the market use aluminum as a way to dissipate heat. It's a great aluminum. It's a great material for that. We've seen copper. A more expensive material, but it dissipates heat just as well. But the heater blocks can range between brass to bronze to stainless steel to copper. The fundamental design is actually quite interesting in that the heater block portion of the hot end, it's about retaining as much heat and holding on to it as much as possible. And then the cold end is about throwing away as much heat into the atmosphere or into the loop as much as possible. And then just in between is preventing the heat from moving up as much as possible. And that's really the fundamentals of a hot end, right? Everything else is about wear resistance of the nozzle. So you have the most typical nozzles are brass, so they're quite wear prone. And then you have hardened steel. You have ruby nozzles, and you go all the way up to titanium nozzles, which are few.
So it really depends on the application that you're looking at. Depending on what you want to achieve with your 3D printers, you might want to look into what kind of, I guess, ingredient or material to use to build your hot end.
So the thing to note with all metal hot ends is that it can do some really crazy thermoplastics. But we have to fine tune the hot ends for those applications. And there are some hot ends that are better for PLA, like a very singular purpose, than there are for one where you design it for multi-purpose. Thermoplastics get sticky when they get hot. And then the interiors of titanium and stainless get sticky when it gets hot. So there's a lot of mechanical characteristics that people have to think about when they're designing a hot end. But generally speaking, if anyone can come up with an idea that keeps the hot end hot, and when I say hot, like 1,000 degrees, The cold end cold, and I mean, when I say cold, like 15 degrees.
Yeah.
And they can put something in between that will prevent the 1,000 degrees from traveling to the 10 degree zone.
Mm-hmm.
They've built a hot end. I mean, I just overly simplified the whole
which
process.
is why when you look at Hotends, you probably see why it looks like there's a lot of those heat sink looking designs on it, right?
Yeah,
just
every single hot end has a heat sink fin and a heater block.
It's just like when you're looking at like computers, like motherboards, you see heat sinks on parts just to dissipate heat faster.
Yeah.
So some hot ends that are on the field has a lot of heat sinks. Like there's like probably like 10.
Yep.
And yeah, those are, I don't know. Do you think it's more efficient having more fins?
It depends. Again, it depends on, I mean, we're going to talk about the engineering a little bit here. It's about the thermal conductivity of the materials, right? Mm-hmm. So the thinner the fins, the harder it is for it to move heat from one to another. Same goes for stainless steel. When you're milling it down to 0.2, it's hard to move heat from one end to the other. So you got to have a balance between material thickness and number of fins that are available. Theoretically speaking, more fins is better, but it's not always 100%.
So if I had really thin fins, like 2 really, really thin ones versus 6 average size fins, which one would be better?
It depends on what the average size fins are.
I don't know, let's take our hot ends for example.
Like a 2 millimeter fin versus like a 0.5 millimeter fin?
Yeah.
I would probably go for a 2 millimeter fin without doing any of the analysis on actual.
But as you said, if it's so thin, then the heat can't go up. So why? How come?
Think about those computer fins. They're really thin.
Yeah.
They can still conduct a lot of heat.
Well, yeah, I know. I have touched them before and literally burned myself.
Well, you probably shouldn't do that. But the way to do it well is to look at the calculations, to do some computer simulations of what the material's density is, what the material's thermal conductivity is. Yeah. And hot ends are a design based around understanding thermal conductivity and thermal dissipation, right? Yeah. If you can manage those two things well, you can actually design a hot end that is really, really good, but real life comes into scenarios because we're in an ambient space and the space may be 35 degrees now.
Yeah.
Tomorrow it could be 25 degrees.
Yeah.
And in the wintertime, it could be 1 degree. Yep. Right. So, variations in the temperature will change how hot end actually operates in real life. And humidity plays a big role for dissipating heat. Yeah. So you will want to over-engineer something that is going to try and meet multiple stages. And that's why a hot end designed specifically for ABS, a hot end designed specifically for PLA is going to work much better than a hot end designed for both of those and more.
It makes sense. It's
master of one.
Yeah, master of one or master of none.
That's right.
Yeah.
Yeah. But it doesn't mean that you can't have a hot end that is really great for upper end thermoplastics that is for 450 degrees and up. Because some of those thermoplastics and engineering plastics actually work very similar. So, I mean, for those that are interested in building hot ends, I mean, that's how you do it. I mean, it's totally oversimplified, but that's how you do it, right? You would look for materials that would help you dissipate heat, and water cooling is a great way. But one thing to keep in mind with water cooling, and we're talking about reliability of hot ends for a second here, is that the second you introduce complexities into the system, failure rates become an issue. So when water cooling breaks, because they have pumps, fans, radiators, water, and then blockage.
Also, if you introduce something as complex as water cooling, then you'll have to redesign your whole printer because it takes up more space.
Yeah. But inside an environment of heated chambers, extreme thermoplastic. When I say extreme thermoplastics, I'm talking about engineered thermoplastics, the Peaks, the Ultons, the super aerospace grade materials. Hot ends like these won't be good enough.
Yes.
Right? So, you should definitely engineer for that to begin with anyways.
Yeah. Well, for our hot ends, we engineered them for strictly PLA.
Yeah. And they work well because they have that peak insulative material.
Yeah.
And if we one day are ever going to go into multi-material, ABS, even the thermoplastics, the engineering plastics, we would most definitely go towards all metal hotends. It makes a lot of sense to do it that way, and fine tune the hotends for the purpose that we're going to use it for. So, well, I think this is just kind of an introduction episode on TinkTech. Hotends are complex.
Yes.
We've oversimplified them into 3 main categories, but that's every hotend designer out there. They're thinking about these 3 elements, right? They're also thinking about heat retention. So in our hotend, there's a silicone sleeve that goes over the heater block to try and hold heat in. You'll see some of them with like an insulative like white paper over over them as well. That has been done in the past. And
then for us, instead of the silicone for the Ditterpole R, we chose to use a brass.
Yep, bronze block.
Heater block.
Yeah.
And so now you don't have to wrap anything around it at all.
Yeah, but that also includes the design of the carriage. The carriage fundamentally changed the dynamics of that.
Yes.
But the idea was we went from aluminum block to a bronze block.
Yeah.
It heats up just as quick, but retains heat better because bronze has a higher thermal. Oh God, I forgot the word. But it holds heat better, and it transfers heat just as well. And I think over time, as hotends improve, we'll start to see some of these more niche hotends be built for specific purposes. Or maybe we'll see that somebody comes up with a perfect design hotend that is able to use all materials without any drawback. But we've yet to see that yet.
That sounds like a fantasy hotend so far.
Perhaps.
Yeah.
Perhaps. Well, I think that sums up this episode of TinkTech. I would love to see what you guys would love to hear about the nitty-gritties of, well, anything within this industry. What we are planning on doing, just as a quick kind of roadmap for the future, I think we're going to talk about gantries, the various different gantries. We're going to talk about resin printers and how they function, and we're going to break them apart. Well, not a machine. We're going to break apart how it actually fundamentally works. We're going to break apart
heating chambers, heated beds,
heated chambers,
like why you need them.
Yeah, and we're going to go into details of just how the actual fundamental technology is built and share some of that with you because I think it's interesting because we live and breathe this every day. So we want to share that with you guys.
Or if there's anything interesting that you guys want us to take a look at regarding 3D printers, like the technology in it, we'll take a look at it and come up with the answers in the next episode.
Oh, break it down.
Yeah.
And share that with the world. Cool. Well, I hope you guys enjoyed this segment. We're going to make more of these TinkTech videos, and I hope you guys stay tuned.
Yeah. So remember to subscribe for this. Click the bell button as well. And also, you can also listen to this on Spotify and Anchor as well. We'll be putting that on as well. And yeah, we'll see you next time then.
For sure. Take care, guys.
Okay.
Bye.
Bye.